Math 3 Lesson Summary Video. Growing or decaying? That is the question. This lesson is a practice understanding task, which takes concepts you have been working on and applies them to new situations. The purpose of this lesson is to model exponential growth and decay and use systems of equations to solve problems. As you go through the first 6 problems on this task, things that you will want to remember. Compound interest. The formula is the amount is equal to the principal times 1 plus the annual percentage rate divided by the number of times per year it's compounded, all taken to the power of the number of times per year it's compounded times the years. Don't forget exponential growth, we always add that percentage rate, and exponential decay, we always subtract the percentage rate. And we've actually used 3 methods for solving all of these types of equations. You can look at the table and make an estimate between which 2 numbers where something happens. You can solve it algebraically using inverses, and we can look on our graph and look for where the 2 parts of the equation intersect one another. We're going to start with number 7. Durham is one of the fastest growing cities in North Carolina. Find an exponential regression model for Durham population, P of T years since 1980. When it says an exponential regression, that means that we're using technology to help us to write an equation that best fits a set of data. So in order to do that, the first thing you're going to want to do is to actually put your data into your technology, whether that be a graphing calculator or an online graphing tool such as Desmos. So the first thing I want to do, I went into Desmos and I created a table and I entered in my data points. So something that you may notice is that I did not put in 2010, 2000, 1990. The reason being is they have determined that we want T to be the number of years since 1980. So if the year is 1980, it's been 0 years since 1980. 1990 was 10 years since 1980. 2000 was 20 years since 1980. And 2010 was 30 years since 1980. So when I did make my table, I made sure to transition that over to the years since 1980 and not just the year. When you go in and you put your table into Desmos, I then want to write an equation using that table. So the table had y1, so I typed y1, and I used x1 instead of just x. And that tells the computer that I want it to use these numbers. It also has a tilde, I'm not sure I'm pronouncing that correctly, the little squiggly. It's not the equal sign. That tells Desmos that you want it to give you a number for A and B with these points. And so I told it I wanted it to be an exponential equation. Some number times some number to the x power using these particular x's and y's. When you do that, it pumps up some numbers about these. So it gives you some parameters. It gives you a number for A and it gives you a number for B. The R squared value has to do with how close the line is to your data points. If we were to actually look at this graph, notice that the equation doesn't actually go through all of the points. We do call this a line of best fit generally because it doesn't always hit all of the data points, but it fits the data, kind of goes in between it. And so we can see that, yeah, it's going the direction of the model. It doesn't hit every exact point, but it's going to give us a good approximation. So if I look at these numbers, what we came up with for our model is P of T is equal to 105,243 times 1.02688 to the T power. And that would give us our model for this situation. Now, use the model to predict when population in Durham will quadruple. So if we wanted to quadruple, we need to think about that word for a second. That means to be 4 times. All right. So if it is 4 times whatever our population was when it started, we want to think about how are we going to figure out how long that's going to take. So if you remember, if it's going to be 4 times, that's that number inside. We want it to be times 4, basically. And so if we had our inside number of our model was 1.02688 to the x power, we want that to equal 4, because that tells us how many times, times 4. So this will tell me how many years I have to make this number end up just being 4 times what we started with. And so I'm just interested in that growth factor part of it. So how long is it going to take for this to equal 4? Again, we can use our algebraic. I'm going to have to do log base 1.02688 to both sides, 1.02688, and the log and the exponential will undo one another, and I get that x is equal to 52.26 years. Now the other thing is, when is that? That's 52 years after 1980, so that would be sometime in 2032 is when we would expect for Durham's population to quadruple. Use the model to predict when the population was half the population it was in 1980. So instead of being equal to 4 times, I want to end up multiplying by half of what it was. So 1.02688 to the x power, when is that going to be equal to half? Well, I solve it the same way. I'm going to do the inverse to both sides. Log 1.02688. These will undo one another, and I end up with x is equal to negative 26.1. How does negative time work? Well, remember, 0 was 1980, so this just means that it was 26 years before 1980, which would have been 1954. Although with the 0.1, you can make an argument for it being 1953. Rewrite the model so that t is measured in decades. So we have, this is our model. We already have 1.05243, 1.02688, and it's to the t power, and that's what it is if we have our growth rate per year. But we want this t to be in decades. So if I think about that, if t was decades instead of years, in order for me to still use this same model, since this growth rate is in years, this would have to be 10t. Because if t was decades, 1 decade would be 10 years, and then this would get multiplied for every year, which is what this rate is based on. The reason we want to do that is because now t is in decades. So I changed t to be decades now. And if I take 1 decade and multiply by 10, that gives me how many years it is, and then I can multiply this. I want to remember that because it allows me to take this number to the 10th power. Remember those laws of exponents that we use to say a power to a power, you multiply. So I can take this number to the 10th power, and it's going to give me a model that is just to the decades. And so for every decade, I could figure out what that's going to be. So 1.02688 to the 10th power is actually equal to 1.3038. So if I'm looking at that, that tells me that my annual percentage rate is 2.688. But my decade percentage rate, how much it grows every 10 years, is actually 30.38%. So that makes sense because over 30 years, I would expect it to grow more than I would over 1 year. And so that makes sense. How can you convert the growth factor from A to B, or A to that in D, and vice versa? So the big idea here is remembering how many times it's getting done. Like, am I changing 1 year to 10 years? What is that actual amount? Another way to think about it is if you're trying to go to if you want to go to a larger increment of time, so like from 1 year to a decade, that's a larger increment of time, I'm always going to multiply up in the exponent. But if I'm trying to go to a smaller increment of time, maybe you're going from years to months, or you're going from hours to minutes. But if you're trying to get to a smaller increment of time, then when we're writing that exponent up at the top, we want to divide. So it's t divided by whatever that amount is. So up in this one, we were going from a year to a decade. So we were going to a larger increment. So I made sure that I multiplied. There's 10 years in a decade, so I multiplied. If I had been going from hours to minutes, I would have said, oh, okay, that's getting smaller, so I need to divide. So I would say t divided by 60, because there's 60 minutes in an hour, so forth, and so on. Number 8. You have landed a new job at Spatco in Raleigh as a mechanical service technician. Spatco is a company that specializes in fueling dispensers, tanks, installation service, POS systems, and more. The pay is $14 per hour. Each year you will receive a raise of $1 per hour or 5% per hour. You need to pick one of their offers. When will the two offers pay the same per hour? All right, so let's think about these two situations. We know anytime we're looking for where two things are the same, we can graph them and look for where they intersect. So I just need some models to work with. For the first one, it looks like I start with $14 per hour, and then each year I receive a raise of $1. All right, so that's a constant rate. And so $1 per hour. So X is my hours, Y is what I'm making per hour. So that's my first situation. The second situation, I start with $14, but it's going up 5% each year. So this year, each year it goes up $1. Here, each year it goes up 5%. So I want to know where and if these two things are equal. So I'm going to take my two equations and I'm going to type those into Desmos, and I'm going to look and see if they intersect. And in fact, they intersect in two spaces. Now the first one makes sense. They both started at $14. So yeah, at time 0, when I first got hired, I was making $14 per hour, and that was true for both of them. So there's one point of intersection that totally makes sense. And then up here, it looks like after 14 years, almost 15 years, so after the 14th year, by the time you get to the 15th year, you made the same amount of money per hour. Now, how would you use that information to help you figure out which offer to take? There's not just one correct answer here. There are lots of things to think about. For these 14 years after you get started, the red line, the straight line here, is going to actually be making more, especially here in the middle. It gets to be like significantly more, somewhere right here towards the middle. But as you get up here, they get closer and closer to one another. And in fact, at year 15, the blue salary is going to start to surpass the red salary, and by quite a bit. It's going to start to get big quick. So the big question when you're trying to make a decision about that is, how long do you actually plan to stay at that job? If this is a job you plan to retire from, it might make more sense to make a little less money at the beginning to make a lot more money at the end, especially because your retirement pay is dependent upon what did you make that last year you worked. However, the average rate for people to stay at a job nowadays is 3 to 4 years. So if you're only going to be working there for 3 or 4 years, you might as well make the most money you can while you're there. So there's a lot of things to think about, but being able to model and look at the situation helps you to make a more informed